All right. So now that we've talked a little bit about theoretical strength and what happens when you have a flaw in a material, I want to look at a person called Griffiths and his approach to how he dealt with this the presence of the flaw and the fracture of the material. So what he did was he came up with an energy balance, and so this was um, a balance between the new surfaces that are created. So if you break apart a material, you now have two new surfaces, and also the strain energy. So you're putting this under tension, and there's going to be strain energy that's released when that breaks. So basically, there's these two factors, and he made an energy balance of these two. So the first one being two new surfaces created, and so this is going to be related to surface energy. The second one here is going to be the strain energy by work that's done from the applied stress, and that's going to be released by the creation of these surfaces. And this is going to be related to strain energy. So this is going to be related to a lot of the elastic theory that you've seen in various classes. So let's take it sort of step by step here then. So the first one, let's talk about the strain energy. And so if you'll remember a very simple stress strain curve. So this is strain stress, so epsilon sigma. And in the elastic portion, the strain energy in the elastic region was related to the area underneath the curve. So basically this shaded region that we see, right? That's what we have. And so we can look at that as an integral of the stress as a function of strain. And we can approximate that. So all this basically down here is just approximating this integral to a very simple relationship of the yield strength divided by the elastic modulus, E. So here this is from a different reference, so I term the elastic modulus E again. But again, keep in mind our book is going to be a little different. So more or less what that's doing is we're kind of taking this area underneath the curve as a triangle, right? And so that's really what we're doing. We're taking the elastic modulus, the yield strength, and the two to look at the triangle here. So that's really what this does. So this is a simplification, but it's a pretty good one when there is no plasticity. So when it's very limited to the elastic region, this is a pretty good approximation. So this was also known as the resilience, if you remember that term from MSE403G. All right, so so that's one of the terms, right? So we have the strain energy, and so the total energy we're going to have of that material, which we take as a plate. So we have a parallelepiped, is going to have a volume V naught, and then we're going to apply a stress. And so here I've went ahead and plugged in what we just talked about with the stress and the elastic modulus. So that's the first portion. All right. So basically here, then when we want to get the strain energy, we can use this approximation. So I'm not worried about the overall derivation, about you understanding each little step, and I won't ask you to derive this at any point. I just want you to know where it comes from. So here we're talking about the strain energy, and so this is again the applied stress, elastic modulus, and then here this is the geometric term. So we have the crack size, and then the plate thickness. So how thick? Let me go back. Sorry, the thickness of this plate, parallelepiped, and then C is if we have a surface flaw, the length of that surface flaw or crack. So that's kind of the area in which is affected. So it can around this surface crack, the bonds can relax a little bit and lose strain energy. All right. So that's kind of accounting. That was kind of accounting for the elastic modulus. And so now we want to look at the other side of the equation. We want to look at the surface energy. And here, the surface energy, which is the term here, the overall energy for this is 2 times. So the 2 just comes from the fact that we have 2 surfaces, and then the crack size and the plate thickness again. So that's a pretty simple version of it, but we have to know the surface energy. Excuse me. So now, when we put this all together, so we have the initial sort of energy here, the term we saw for strain with the relaxation term, and then also the surface energy term. And so when we have these two, these are balancing out. So the surface energy increases energy in the system, and then the elastic energy decreases the energy in the system. So we see this, again, maximum occur in a certain spot. And so that maximum is important to us because that maximum refers to the x-axis, which is the crack size. And so that talks about how large, what is the critical size of crack that's going to cause failure in the system. And so in this case, we see that the critical crack length C is quite large. So on this scale, it's 1, 2, 3, 4. And then if we go here, if we apply a greater stress, then we see that that critical size becomes smaller, right? So it's 1, 2. If we increase the applied stress by square root of 2. So what that says is that if I apply a greater stress, it takes a smaller crack to cause failure, right? And that's important for us to know, right? We want to know what is the dependency of crack size on the overall material. And so again, this is the certain crack size at which it becomes unstable. So once it reaches this critical value, it becomes unstable, and that's basically when we have that unstable failure of the material. And so that is in this case in each term. All right. So, but we want to kind of get it into a useful form that we have. So basically, if we differentiate that total energy, and then we actually equate it to 0, and this will give us that critical crack size. So basically, just what you saw in the graph there. So we have this critical crack size here, and then we have pi, and then we have the failure stress here, and then on the other side, we see that this is in terms of the surface energy value and the elastic modulus. So basically, what we've done here is that we've gotten everything. There's a material property, surface energy, elastic modulus on one side, and we've got everything that's sort of process dependent, crack size, and the failure strength on the other side. So each of these sides is known as something. So the left side here is known as the stress intensity factor, right? Kind of telling us, named this way because it's telling us, we apply a certain stress, what is the intensity of that stress, because we do have flaws, right? So we call that stress intensity factor, or K1, and 1 refers to the type of stress state that we have, and we'll talk about that in a second. The other side is known as the critical stress intensity factor, or also fracture toughness, and this is K1C. So the C here stands for critical. And so this is something that we can calculate or estimate for given materials. And so basically what this sort of equilibrium shows is that we will have failure when the stress intensity factor is equal to or greater than the critical value, right? That's basically what this expression is showing us, is sort of a balance of when will failure occur related to some material properties that we can try to estimate. And so one thing I will note about this is it kind of has particular units because we have stress multiplied by square root of length. It's going to have those units. So megapascal times meter to 1/2. So it has kind of interesting units applied here. All right, so this allows us to, again, use some material properties to determine when failure will occur, and based on the size of the flaw as well. So we have that connection between applied stress, flaw size, and when failure will occur. All right, so all of that derivation that we did is assuming that our elastic material is completely elastic. There's no plastic deformation. Excuse me. So for ceramics, this is a pretty good approximation, right? We don't expect plastic deformation to occur, but some plastic deformation can occur at the crack tip, and that will dissipate the energy, and so that will change the values. Also, at elevated temperatures, more and more plastic deformation tends to occur, and so those values can change. And so the critical value then, the critical stress intensity factor, K1C, is then equal to the square root of the elastic modulus, and then times it's changed to the toughness. And so this accounts for the plastic deformation that may occur at the crack tip. So we can modify that expression if we have plastic deformation. All right, so what we're going to do now is see if we can apply those equations that we just looked at. So I've got some data tables here. You'll also note that the critical stress intensity factor is actually here too. So ignore that. I mean, you're trying to calculate it, so don't just use those values. But see if you can calculate the critical stress intensity factor for glass, and I'll let you make your call on what glass that is. State any assumptions that you make. That could be based on glass. And then, again, I've given you some data tables here, one from the book and then one with surface energy calculations from some sources on Wikipedia. So see if you can go ahead and calculate those values, and we'll come back and see what we get. All right, so we've had a chance to look at this calculation for critical stress intensity factor for glass. So let me go ahead and move to the next slide and show you what this looks like. All right, so the critical side, again, was that right side of the equation, K1C. And so we saw that that was related to the square root of 2 times the surface energy times elastic modulus. All right, so from those tables, for the surface energy, I used the value for glass. There was only one value given there. So you can see this 310 millijoules per meter squared. So I've turned this into SI units, so joules per meter squared. So I put the 10 to the minus 3. And then I've multiplied it by the elastic modulus for glass. And so in this case, in this table, you'll notice that I use the soda lime silica glass. So you had some different values here. For me, I just chose to use a very simple composition of soda lime glass. So that is a 69 gigapascal elastic modulus. And so 69 and then 10 to the 9 for the giga. And so if I put that all together, I get 206,833 pascals per meter to 1/2. And so if I want to get that into more useful comparable units, that would be megapascal per meter squared, or sorry, square root. And so that's 0.206 megapascal square root of meters. And so if you compare that to 11.1, so if I go back and look at soda lime glass, I'll see that my K1C value for that is 0.82. And so my value here is a little off from what they had. So that's, we can always kind of compare our values, but this one's a little bit off from what that is. And that could be a number of things. We're assuming this sort of glass for the surface energy, but we're not telling us what type of glass. And so there's some error there. And so forth. So we're having to make some assumptions with this composition. All right, so now let's get to the second part. So we've calculated this critical value, and so now I want to get to more maybe of a practical problem. So let's say that we have that plate of glass again, and we have a surface crack in it, and we want to calculate the smallest surface crack length. So, using those figures in the previous slides of a plate of glass with a crack in it and with the surface crack length C in it, if we subject that piece of glass to tensile stress at 150 megapascals, see if you can calculate what the smallest surface crack length has to be for failure to occur using what we've just talked about in this section. So tell me any assumptions you make. You can go ahead and use the critical value in the table for this one if you don't want to use the value that we just calculated. So take a few minutes, see what you can come across, and then we will come back and look at the answer. All right, so hopefully you've had a chance to look at this. And so now we look at that whole version of that Griffith energy balance. And we already did the critical value on the right side. So we calculated that. We can also use the literature value in this case. And now on the other side, this is where we get to crack length and the failure strength. So we're kind of trying to relate the critical value to this. And so we know that when this value is greater than or equal to this value, that failure should occur. So I'm going to set them equal to just to make it a little easier for us. And then what I'm going to do is I'm going to rearrange this expression to solve for the critical size, because that's what we're looking for up here, is the smallest surface crack length, that will occur. So if I rearrange it, I get 2 surface area times the elastic modulus over pi, and then the stress squared. And so if I put in all of these values then, so here instead of using the literature value, I'm going to plug in the same values I used. So 2 times 310 times 10 to the minus 3 joules per meter squared. And then the elastic modulus again. And then on the bottom here, I'm putting in the applied stress. So 150 megapascals, so 10 to the 6. And I'm going to square that. And I get, this should come out in meters. I should get 6.05 times 10 to the minus 7. And so that is 605 nanometers. So that is the size of flaw. That's the smallest size that would cause failure in this material. Any smaller, we wouldn't expect failure to occur. Larger, and we would definitely expect failure to occur in those cases. So this is the critical value that we have, right? Because we're setting it equal instead of talking about the larger value.